Hi. This was supposed to be an addendum to the current video, but I figured that some people speed view these things and may miss this at the end of the video, so I thought I'd sneak it in at the beginning and put a semi-interesting picture, a partial picture of my collection of data books and other reference materials I use. But what I want to talk about briefly and specifically is donations to the channel. I used to be able to get good deals at thrift shops and surplus stores and all of that, but recently it's become very difficult for me to find good stuff. For two reasons. Everybody and their brother seem to be out there collecting and buying stuff and camping out at the store all day. And second of all, around here, at least where I live, most people seem to be too proud to wear masks, and I'm kind of hesitant in going into a lot of those places that are mobbed by people who don't wear masks. So anyway, the only thing remaining for me is to go and buy these things through eBay, which are getting more and more expensive, and of course, to ask for donations. So if you have anything that you may think could be an interesting subject for a video here, to either take apart, fix, or just have a good time with, let me know, and it would help the channel a great deal. The way to contact me is I've set up an email. It's called afdonations@aol.com, and you can reach me directly through that, but please limit your communications to donation-related stuff. And because everything else I will probably ignore because it belongs into the comment sections. Thanks for listening. Greetings. This is Artie. And finally we're at the point where we get all the prerequisites out of the way and we can actually get to executing some 6800 code and looking at all the wonderful instructions that are available to us. So what we're looking at here is really in two parts. It's something I wrote, well, the base of this I wrote a while ago. It's a 6800 code simulator. It's written in C# for the Windows environment. This over here is a code window. It shows us the program counter or memory address that contains the next instruction to be executed. In this column, there's the actual machine language or the machine code that is sitting at this memory address. Really all you do with this is it has an internal RAM buffer that simulates both RAM and ROM for a 6800. And all you do is you write your program, you assemble it into a binary file, and then you load it in here. And this column is actually what's contained or would be contained in a binary file. And this column takes it and does something to it called disassembly. It takes the machine code and shows you the assembly language equivalent of it. In this case, RAM is all filled with the value 1, hexadecimal 1, or remember, in small numbers doesn't really make a difference, decimal 1 or hexadecimal 1. It'll make a difference soon, but not while you're looking at this window. And it's full of, the 1 happens to be the no-op operation, which stands for no operation, and that's really what it does. It doesn't do anything. Well, the one thing it does is when you execute this instruction, it will advance the program counter by 1 and then execute the next operation here. So if you were to execute this, it would just run, do no ops all day long. And assuming that all 64K of the address space are filled with no ops, it would just do no ops 64K times and then wrap around back to address 0 and do it over and over and over again. But that'll give you an idea of what this environment will be doing for us. The other things are, we have a memory window here that can be used to display what's in memory in any of the in any area in the 64K of simulated memory that we have, which can contain either RAM, ROM, peripheral chips, all sorts of stuff. And then this is a duplicate of the machine of the programming model. And this will actually tell you what the registers are currently set to. And that's so much for the simulator part. We then have a bunch more stuff. And starting with this is a Heathkit ET-3400. Well, it's a picture of an ET-3400 6800 trainer. This was sold in the early to mid 80s. And I mean, this is a 40-pin chip, so that'll give you an idea of the scale, what this is really like. It's in a blue plastic box. You could buy this as a kit or factory assembled. And it was a trainer. It gave you an environment where you could enter code, execute it, single step, set breakpoints, and even better than that, it had a breadboard down here, so you could build circuitry on here, and the address and data lines of the processor and some of the control lines were brought out through these connectors over here, and you could control the hardware and observe for real, not simulated, not emulated, but in real life, how a circuit addition could be driven by a 6800 processor. It also has some LEDs here that are simply LEDs with limiting resistors, and you can utilize those from your circuit, or you can hook them up to the data bus or the address bus and just see them blink or flash. Other than that, it has a keyboard. It's a hexadecimal keyboard, goes from 0 to F, and also has a reset key here. And that is sufficient for its purposes because there's no escape key or idle key or whatever. But whenever you do stuff and you want to start over or get the system back to a known state, you just hit reset. It is non-destructive as far as user memory is concerned, so if you've entered code or whatever, and it's off doing something weird because you made a coding error or whatever, you just hit the reset button, and everything goes back. It acts as if you had just turned it on. The way it communicates with you is through 6 7-segment displays over here, and if I had more time, or I wasn't as lazy, I would have made this keyboard and these displays functional right on top of this. But I try to be more economical with my time, and it was easier and quicker for me to just create my own 6-digit display over here and a keyboard here. That is functionally in the simulator. The simulator will look at the output of this keyboard and will write to these displays. I mean, the displays do simulate the way these work in real life, and we're going to see that a little later because we're going to use some of the example code that was run on the ET-3400, and the example code will utilize these displays correctly as well as read the input from this keyboard. So this is a total dummy. It doesn't do anything, but it's there. It's just there to remind us when we are simulating the ET-3400, of course, what we're simulating. Other than that, we've pretty much looked at everything on here. The only remaining things are as a bunch of decoding chips on here, stuff that's necessary for the processor. This one looks kind of interesting. It looks like the crystal's missing on this picture. Yeah, other than that, there's a ROM here, and that becomes significant because what we're going to do is we have an image of this ROM that we're going to load in and let the simulator execute this ROM, which means that the display should become live and the keyboard should become live. So let's give that a try. But first, wouldn't it be nice if we actually had a real physical ET-3400 on the desk? Yeah, it would be, but I don't have one. So if you have one languishing in a closet or in the garage that you don't need anymore, please consider donating it to the channel, because if one turns up, I'll make sure to have at least one episode where we're going to use that thing and actually build some circuits on it and have them run in real time. Okay, end of tin cup rattling, and on to the real meat of this. So I'm going to jump around a little bit because there's a lot of ground to cover, but as I said before, right now we're in the simulator only. This isn't active. This doesn't do anything. These buttons don't do anything. That's because it's not running any code. The simulator is idle. If we look at this, it says where the PC is. It's not here. And that it's stopped. It's not doing anything. So first remember, it has all of the debug statements available that you would expect. And one thing we can use is prove to ourselves that no op doesn't do anything. And since we're here, we can single step through this. And the single step hotkey is an F11 on the keyboard. And as discussed before, if we hit F11, we will see that the program counter is now set correctly to 1. It did a no op. It didn't change anything. And as we hit the F11 key, we'll see the program counter increase, but nothing else is changing because no op doesn't do anything. So now finally back, we need to load this ROM into our simulator. And we don't have one, so we're going to simulate it. But as we'll see later on, even though this is a wonderful training device, it does have its shortcomings. And those shortcomings can be overcome by looking at the simulator output. For instance, it uses 6-7 segment displays to communicate with you. You're not going to see a program listing on here. Well, I guess you could see a single line, or as much of a single line as you can fit into it. Yes, you can fit a no op into it in the code 01, but that's about as far as it'll go. And what we'll find out is that it's actually much more convenient to look at code in the simulator itself, in this window. But for now, let's assume that all we have is an ET-3400. And the way we get into the ET-3400 is there's a project file for this simulator. And it has specific fields for the ROMs that you could run in the ET-3400. The first one, of course, is the firmware or the BIOS, the one that we saw in the picture. I have 2 other ROMs for it that came. You could buy an expansion box for the ET-3400 that had more memory in it, had a serial port on it, all sorts of goodies. The first one was called the Phantom 2 ROM, and that was a machine language monitor, but the difference was it did not run on these displays, but rather use the serial connection, so you had to hook it up to a terminal. A dumb terminal would have worked just fine, and all the communication came through the terminal. And in addition to that, it also had another ROM that ran Tiny Basic. Now just imagine you had to run a basic program using these displays. That wouldn't have worked too well. So the basic also runs through the serial connection. So you would do all of your work on the terminal. I don't have that expansion box. It would be, I can add it. Obviously the simulator, I can add anything I want to the simulator. But for now, suffice it to say that we are going to use the original BIOS chip or firmware that came with it. When we exit the project window, it will go ahead and load the code that was specified in the project. It will then set the program counter to the reset vector. The reset vector is contained at hex address FFFE and FFFF. That is permanent. So when the processor gets reset and the reset signal goes inactive, it will fetch those two memory locations, build a 16-bit address out of that, and that is where the first instruction is that the processor executes. Alright, the code is loaded. What we need to do now is essentially start the simulator. We gave it some code, and what we're going to do is we're going to have the simulator run this code. Now remember, it's running the original firmware, so we should see something happening on the display, and we should get some sort of response when we use the keyboard. So the run command is F5, so we click run. So what happens? Well, this is the normal behavior. Basically, this is the hello world or CPU up. That means everything went great, this thing booted up, and it's ready for keyboard input. Now, one thing you'll notice is that there's a very slow update rate on this half, and that's because it's not updating for every instruction. That will make you sick. The simulator is running pretty quickly, so I already had to put some delay loops in there after executing every single instruction because it was executing way too fast. And still, if I updated this window after every instruction, you would just see things jumping all over the place. So the refresh rate for this window is essentially 500,000 machine cycles. So what it does is it counts the instruction cycles, how long it takes for each instruction it's executing, and when it hits 500,000, it updates this. So that, and I can adjust that, but you know, that's okay for now. It does update the values in this window over here. But see, it's not really doing a whole lot. All it is doing, as we'll see later, is it's sitting in a loop waiting for keyboard input. It doesn't run an interrupt routine. The displays are not scanned, but rather they're latches for each of the display. So all this thing has to do is to write a value for each display, and it stays in there. So even if we stop execution of the program, so if we go to debug break, it'll break at the current location or stop. This stuff remains because it's not scanned. It was latched and it'll be here forever. Now if you had a device that was actually scanning the displays in real time, the display essentially would go blank when you stop the simulation. But in this case, it doesn't because it is latched and the simulator isn't running anyway, so the display probably wouldn't go blank if they were displayed, but you would see the instantaneous value of it. So there would be some segments missing. Whatever segments were on when you stopped the program would still be shown here. It's almost like taking a snapshot in time of it. Now we can go back to run and it'll just continue from where we stopped it. And the shortcut key for that is F5. So if you hit F5, it just continues along its merry way. It goes back to running over here, CPU up, and it's waiting for input. So let's look and see what a couple of these things do for us. Well, first, key 0, it's not waiting for a number, so 0 doesn't do anything in this mode. Now if we click 1, accumulator A, it'll print out accumulator A and the contents of it. And what we can do now is we can change the contents of it by pressing this. And now the keyboard truly turns into a hexadecimal keyboard, and we enter 2A into it. Now our accumulator A contains 2A. Now how come this didn't get changed? That's because this is user. This is a user space, user data, and what we're seeing here is what the simulator is actually seeing. So it keeps a separate copy of the registers for when you're running your own programs. And this goes on. We have accumulator B, we have the program counter over here, the index register or the X register, the condition codes, which are shown as zeros or ones. Notice that it won't let you change the condition codes because you can make things crash horribly if you're just doing that, because it'll interfere with what the firmware is doing. We can look at the stack pointer, and then the other things are more debug statements, but that'll just show you that this thing is running. And as I said before, at any point in time you can click reset. It goes back to the sign up message, initializes whatever it needs to initialize, but it hasn't touched the user area yet. So if we observe accumulator A, it is still a value of 2A. So that stays in there. Okay, now it's time to actually enter our first program into the simulator. Now remember, there's two ways of doing this. If you're actually developing hardware, you would use an assembler to write it, create a bin file, use the bin file to burn an EEPROM, plug the EEPROM into your hardware, and run your hardware and observe and see what happens. Now we do have, we could do that, but that would be overkill for our first program because it consists of what? 6 bytes, 7 bytes. So what we're going to do is use the trainer's capabilities to enter that program into memory. I have the whiteboard sitting next to me that we created last time, and let's run the trainer. Boom, we're up and ready to go. And the trainer gives us a method to enter code in here, byte by byte, but it automates it a little bit. And that is the auto function. We click that, and it basically tells us, okay, the first thing, it says AD, which means enter an address, and it wants the address of where we want to start entering code at. That is 0. And so it tells us the memory address and then prompts us to enter a byte of data. So looking at the code we generated, we start with 86, and notice once we enter a byte, it immediately advances to the next memory location. So all we got to do is keep entering the bytes, so it's not as painful as it might have been. Let's see, so 4A, 26FD, 26FD, and finally 20FE. That's the machine code we generated last time. Now, we will see one of the main shortcomings of the trainer, that is, we have no easy way of showing what the code is we entered. We can verify that we entered the right stuff by using the examine function and again entering address 0, and then using the forward or backward to make sure that we entered the correct numbers. And it looks like we did. Now we can also execute this, but we're not talking to the displays or anything, so we're really not going to see anything change on the trainer. For that, we're provided with the do instruction, and you enter the starting point of what you want to execute, it sets up a few internal pointers and clears the display. So we enter address 0 again, it blanks the display, and disregarding this window for a minute because we don't see that on the trainer is basically nothing's happening. We can't observe. We don't know if it's running or not. Well, we can if we look. Well, no, we can't because we don't see this trainer. We don't see the programmer's model in the trainer. However, if we turn back and we do look at the simulator, we can see that the program counter is basically stuck at 5. It does say that it's running, but notice the instruction says branch to location 5, which is itself. So all this is doing forever and ever and ever is branching to 5. So what does the code look like in its entirety? Well, for that, we need to stop the trainer, drop back into the simulator, and set our program counter to 0, because that's where we entered our code. And now we see that the code we wrote is entered at location 0 and looks exactly like what we created. And now what we can do in the simulator is actually step through this code, one instruction at a time, and observe and see what happens. Now notice that the memory window is actually showing our machine language, our machine code over here, which corresponds to what we're seeing on the code screen, and then the rest of them are still filled with 1s, which are the no-ops. If we just executed this in the simulator, we would see pretty much what we saw before, that it would just execute this lightning fast and then get stuck on this instruction. But in the simulator, we can single step it and look in the register window and actually see things happen. So let's do that. If we look at the instruction, well, it's called step into. There's a step over and a step into, and we will differentiate between these two as we look at more complicated code. But for now, we're going to use the F11 hotkey to single step. Our program counter is pointing at the first instruction. We execute it with F11, and as expected, see the accumulator A now holds 4. Next we do a decrement A, and that should decrement this number by 1, and that's what it does in fact. And now we come to a conditional jump, or a conditional branch, and it says if A didn't get decremented to 0, branch back to the decrement instruction. Here's the address, and here's what's in that address. So if we single step again, we go back to the decrement instruction, and observing the accumulator value, as we do this, the accumulator eventually reaches 0. Now, we need to look at the processor flags, or condition codes, and each instruction sets the condition codes, sets either none or some of the condition codes, and that's dependent on the instruction. We're not going to go through that. When you start writing real code, you need to download a copy of the 6800 programming manual, and that will describe in excruciating detail how every instruction affects each of these flags. In this case, all we're interested in is that the decrement A instruction, when we decrement it from 1 to 0, set the 0 flag to 1. The conditional branches are dependent upon the condition codes. And before, when we ran this, it jumped back up again because the 0 flag wasn't set. But now that we decremented it to 0, the 0 flag is set and this branch is not taken. It simply increments the program counter by 2 kind of like the no-op, because when a branch isn't taken, it just falls through. So when we hit F11 again, this time we land on 5, and now we can hit F11 all day long, and nothing's going to happen, because it keeps jumping back to itself. Congratulations, you just saw your first 6800 program being single-step through in its entirety. Now remember, there were some programs given in the user manual for the trainer, which are quite useful, because you don't have to write them yourself, and they supposedly work. And, of course, first when you see those programs, you go, oh no, I got to use the auto function to enter these things byte by byte. And when I turn this thing off, they're going to be gone. But what we do is, Simulator has a neat feature where you can save and load the contents of RAM. So we can go to Load RAM. And what I'm going to do is load sample 3, and that's because sample 1 and 2, notice they all start at different addresses. All 3 of those are contained in this file. So I load this file, and if we look at 0, we now see something a little bit more sophisticated in here than what we saw before. We can execute it from here, but again, let's first execute it from within the trainer. So we do a reset run, we're ready to go, and remember we used the do function, or the do key, to jump to the beginning of this program. It is at 0, and observe what it does. It lights up every segment and every digit. That's all it does, forever and ever and ever. So once it's through, it just starts over again. And I thought about this long and hard, but instead of going through every single instruction available to the 6800, I figured we could step through those instructions in the simulator mode, and I would kind of explain the instructions that we encounter and what they do. And that'll give you a pretty good overview of all of the instructions available. But since we have stuff sitting here, remember we loaded in, there's actually 3 programs here. We see the next one start at 30. So let's go ahead and stop this. And this time, go to location 30 and see what it does. The second sample program. Oh, and all this does is it blinks all of the displays on and off. There you go. No big deal, but this kind of teaches you how to talk to the displays, this in the preceding one. And we also have a third example that starts at hex 60. And this one actually talks to you. This is like an expanded version of the sign-on message. Instead of CPU up, it says your 3400 is up and running. So by this point, we obviously know there's code that tells you how to deal with the display. But let's go back to the one that turned on all the segments and look at that in a little bit more detail. Okay. Again, time flies when you're having fun. So we're at the end of class today. Pack up your books and go play. We should have a better idea after this one. We've actually seen 6800 code executing. Have a little better idea of what it's like to execute it in tester or in trainer mode versus just raw simulator mode. What we're going to do next time is look at our first example program, the one that shows all of our segments being lit. And we're going to step through it in simulator mode. We'll encounter some new instructions and analyze those, and also encounter some of the neater features of the simulator. So, like, subscribe, share, comment, walk across the room on your hands, and we'll see you in part 4. Bye.